So, okay. Now, the corresponding principal minor is just the determinant of this principal submatrix. So, for an n cross n matrix, there will be 2 raised to n subset of the index set. So, there will be 2 raised to n principal minors. And now, two matrices A and B are said to be principal minor equivalent if all these 2 raised to n principal minors are same. So, here is an example of two matrices which are principal minor equivalent. The principal minor corresponding to singleton sets correspond to the diagonal entries. Note that for these two matrices, the diagonal entries are same. And for all other subsets of the index set, we can also verify that these are same. We will see this example later again in the slides. So now here the goal is to decide whether these two matrices are principal minor equivalent or not. So for this problem, there exists an efficient randomized algorithm. And so in this slide, I will explain what is this algorithm. So suppose A and B are our input matrices, and X is a diagonal matrix of same dimension, and its diagonal entries are distinct variables. So there will be n variables here. Now the claim is that these two matrices are principal minor equivalent if these two polynomials are exactly same. So a brief proof sketch for this is that note that in these determinants, each variable occurs at most once. Hence, this determinant will be a multilinear polynomial. And the coefficient corresponding to a particular monomial is just the principal minor corresponding to its complement. So this says that the coefficients are exactly the principal minors. So this means that checking whether these two matrices are principal minor equivalent is same as whether these two polynomials are same. And in the last talk, Robert mentioned that checking whether two polynomials are same, we have an efficient randomized algorithm, and that is by Schwarzschild lemma. And in this algorithm, we will just choose a random point and evaluate these two determinants. And if they are same, then we will output that these two matrices are principal minor equivalent. Otherwise, we will say they are not. So now, in this work, we give a deterministic polynomial time algorithm for this problem. First, I will mention some previous works for special classes of matrices for which there were already results known. So in the next few slides, I will mention some definitions. So first of them is irreducible matrices. So here first see an example of two matrices A and B. Here A1 and A2 are A1, A2 and B1, B2 are principal submatrices of same dimensions. Now, suppose here is the case that B1 is same as A1 and B2 is same as A2. Then these two matrices have same principal minors, irrespective of whatever the entries of this matrix is B3. So we can generalize this statement and say that A and B have same principal minors if and only if the pair of matrices A1, B1 and A2, B2 are principal minor equivalent to each other. We can generalize this even further for reducible matrices, which I will define now. So a matrix is called reducible if we can permute the rows and columns simultaneously so that we get a block upper triangular matrix. So this will be more clear with this example. So here is this matrix. And now we will exchange second row and column with third row and column simultaneously. Then we will get this matrix.
In the second bullet, you say B1 equals A1, and the third one say A1 equals
Equivalent. So they were the principal minor equivalent. I mean, they have same A1 and B1 has same principal minors. So this is because for any of this principal minor, if it is a subset of index of set of A1, then it's like if they're principal minor equivalent, then it's fine. And if it's like union of like some subset of union of A1 and A2, then it will be like product of these two principal minors. And since A1 is principal minor equivalent to B1 and A2 is principal minor equivalent to B2, their product will be also same. Yes, yes. And this reducible property will subsume this one, because we are just saying that there will exist some permutation. After doing this permutation, we will get a block upper triangular matrix and something like this. So B1 and B2 are blocks, and whatever irrespective this entries of B3 are, we are fine. Yes. Yeah. 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 That will not be reducible. It will be called irreducible matrix. Yeah. Yeah. So checking, so another easy way to see whether a matrix is reducible or irreducible, we draw a related graph. So here the vertex set is the index set of the matrix, and there is an edge from vertex I to j if the matrix entry in ith row and jth column is non-zero. So for example, so let's see at this entry 2. So it means that the entry in the first row and second column is non-zero. So that's why there is an edge from 1 to 2. However, this entry is 0. So there is no edge from 2 to 1. And a matrix is reducible if and only if this underlying graph is one strongly connected component. Otherwise, these strongly connected components will correspond to these blocks. And in 1984, Hartwell and Lewis showed that for reducible matrices, we just only have to care about these strongly connected components and individually check whether the block matrices corresponding to this strongly connected components are principal minor equivalent to each other or not. So now I will define another term which is called cut of a matrix, which is defined for irreducible matrices. So a cut of a matrix is a subset of the index set of size at least 2 and of size at most n minus 2, such that these two submatrices have rank exactly equal to 1. Note that this is the minimum rank possible, because if it is 0, then it will be a reducible matrix. So here is an example. This is the matrix A, and we are considering this subset 1 and 2. So the first submatrix correspond to this rectangle, and the second submatrix correspond to this rectangle. And these two matrices have rank 1 because there is only one non-zero entry. Now let's look at another set which is not a cut. So the first submatrix correspond to this orange block, and this orange block does not have a cut. So this is not a cut. Now I will define some matrix operations that preserves principal minors. So one trivial operation is just taking transpose of this matrix. And another not so trivial operation is that we multiply the first row by some non-zero scalar and simultaneously divide the first column by it. So why this is true? Because the principal submatrices which does not contain first row and column, they remain exactly the same. So the principal minors will also be same. Now if we consider the principal submatrices that contain first row and column, so and when we expand its determinant using Laplacian formula, then each term, this d and 1 over d will cancel each other. So that's why they will have same determinant value. And we can generalize this operation by multiplying A with some invertible diagonal matrix on left hand side and multiplying with its inverse on the right hand side. So here what we are doing, we are multiplying ith row by the ith diagonal entry of this invertible diagonal matrix T and simultaneously dividing ith column by it. And we say that a matrix B is diagonally similar to it if we can, if there exists an invertible diagonal matrix such that it is equal to D times A times D inverse. Now this is the example that we saw in the first slide, and they have same principal minors because B is diagonally similar to A. So now I will mention some results that are known for principal minor equivalence for reducible matrices using these definitions. So in 1980, Angel and Schneider showed that, so suppose for an irreducible symmetric matrix A, another matrix B has same principal minors if and only if it is diagonally similar to A. Now, few years later, Hartfield and Lewis showed that for an irreducible matrix A which does not have cuts, they are principal minor equivalent if and only if B is either diagonally similar to A or diagonally similar to its transpose. So there are also other results, but these results were related to by putting some constants on the matrix entries. I will not going to mention these results. So note that the only case left here is that when the matrices are irreducible and they have cuts. So recently, Amadia showed that these two principal minor preserving operations are not sufficient for matrices with cuts. So she defined another principal minor preserving operation. And for that, we will first see what is the determinant of a matrix with a cut. So here is this input matrix, and suppose S is a subset of the index set, and it is a cut of this matrix. So what do you mean by this cut? So cut means this submatrix has rank 1 and this submatrix has rank 1. Since they have rank 1, they can be written as a dot product of two vectors. So suppose it is P times Q transpose and this submatrix is U times V transpose. Then C showed that the determinant of this matrix is represented by the following formula. So note that if either of these orange submatrices was the zero matrix, then we get a reducible matrix, and their determinant is just the product of determinant of this principal submatrices M and N. And now this formula generalizes for matrices with cut. And now in the second term, we get these two submatrices. And this first matrix is obtained by adding one row and column to principal submatrix of A. And this second submatrix is obtained by adding one row and column to this principal submatrix N. One more observation here is that this matrix is very similar to one of the principal submatrices of A. And this observation we will use later. And now using this formula, Amadia defined another operation which we call cut transpose operation that preserves principal minors. So here is this matrix A, and this is the this represents the cut of this matrix, and this is the formula from the previous slide. And now how this cut transpose, the matrix obtained by taking cut transpose operation is defined. So M is just as it is. Here we exchange these vectors U and Q with each other. So note that here instead of Q we have U, and here instead of U we have Q here. So, and another change is that instead of N we are replacing it with its transpose. Note that now again whatever the this cut was, this matrix A has this cut. Now again this matrix B also has the same cut. And now using this formula, we can again write the determinant of this matrix B, which looks like very similar to this. And now we will compare this. So note that these first terms are same, and here with in place of N we have N transpose. So the first term is same. Now we look at the second term of the summand. Again the first matrix is same, and the second matrix is transpose of each other. So that means The second term is also same. This implies that these matrices have same determinant. And this we can argue for any principal submatrix of A and N, of A and B. So they are principal minor equivalent. So like I mentioned earlier, the only case left is for when the input matrices are reducible and have a cut. First we will see a very simple case where the input matrices are irreducible and have a common cut, and we will try to figure out what can we do in this case. So A and B are input matrices and they have this common cut, let's say S. So the result of Hartfield and Lewis showed that if either of this orange block matrix is 0, they are principal minor equivalent if and only if M1 is principal minor equivalent to M2 and N1 is principal minor equivalent to N2. And in this work, we showed that if they have a cut, then A and B have same principal minors if these two matrices are principal minor equivalent to each other. So note that these are the matrices that we got in the formula in the previous slide. And yeah, so this is the result. And if that is the case, then we can reduce it to a smaller instance of principal minor equivalence, where now the sum of the smaller instances is roughly equal to the size of the original matrix. So this is just like mod S plus 1, and here it is mod S complement plus 1. So, and now we can recurse on these two smaller instances and we will get a deterministic polynomial time algorithm. So another question is like, how can we find such whether there exists a common cut S or not? So suppose in this case we are assuming that we are given that S is a common cut. So now the natural question to ask that whether this is always the case when two matrices are principal minor equivalent, when there always exists a common cut or not. So in our work, we saw that this statement is exactly not true, but we show something very similar to it. And we show that suppose A and B are two matrices with same principal minors, and suppose S is a minimal cut, that means there does not exist another cut which is a subset of S. Now, if the size of this subset is at least 2, then we show that S should be also a cut of B. And now suppose if the size of the minimal cut is 2, then one of these two cases happen. Either S is also a cut of B, or otherwise for this matrix B we can find another cut, and now we take this cut transpose of B, then S becomes a cut of this matrix. So now we will again get another matrix A and say this B prime, where they have same cuts, and so again we can now recurse. So I'm not talking about how will we find these cuts and how will we find this cut X in case we are not able to find a common cut. But in our work, we saw that all of this we can do it in polynomial time, deterministic polynomial time. And then we can recurse on these smaller submatrices. So this is the overall idea of our algorithm. So now I'll mention some related problems. So the randomized algorithm that I mentioned, that was sequential, and we can also make it parallel because we just have to compute determinant of a matrix by putting random substitution. So Archit mentioned that the class of problems and this computing determinant comes in NC class. So this randomized algorithm got us an RNC algorithm for this problem. In a recent work, we gave a deterministic parallel algorithm for that. That means deterministic NC algorithm for this problem. Now, a related open problem for this is principal minor assignment. So here we are given an unknown matrix A and we are given an oracle which takes a subset of the index set and output the value of the principal minor. And here the goal is to find another matrix B which has same principal minors as of A using only polynomially many queries. So yeah, this problem has applications in machine learning related to determinantal point processes, which I don't know much about. So yeah, but this is the major open problem related to this. Yeah, thanks. Huh? Yeah, for this principal minor assignment problem, for special classes of matrices like symmetric matrices, or some when we put some constant on these matrices, like their entries are 1 and 0, -1 and 1, skew-symmetric, something like that. And for all those matrices for which this problem is solved, they use this characterization result, or how we test this principal minor equivalence in the deterministic setting. So hopefully, since we have result for this general class of matrices, we are hoping we might get something for the general class of matrices. Yeah, that's it. Yeah. So this recent work, we solve a black box version of this problem. Okay. Yeah. So if you consider this bipartite graph and bi-adjacency matrix, so that will mean that they have same set of perfect matchings. Yeah. For general graphs, I'm not sure. Yeah, so they mean something in terms of metroids. If we work over finite, if we work over this binary field, they will say that all these bases have same bases of these two regular metroids are same or not. But I don't know how it is interesting for.
Any more questions?
Mhm.